Hello everyone and welcome to day 1 of Logarithms. This is unit 8. And Logarithms looks at how to solve exponential functions that we cannot solve with exponents that we understand. And so today we're going to be looking at graphing those logarithms and what it looks like. So let's start with exercise number 1. The function f of x equals 2 to the x is graphed on the axis below with its table. It asks, is this function 1 to 1? If we remember what 1 to 1 is, 1 to 1 says that for every x there's one y, and for every y there's only one x. And by looking at this and looking at this graph, we should be able to say yes. It is 1 to 1. It actually passes the vertical and, well, that's an awful way to write that. Let's try it again. This is the vertical and horizontal line test. It's also because there's one x and one y for each value. Based on this function, or based on this answer from part A, what must be true about the inverse? The inverse is a function. We had talked about this already before in the beginning of the year. And so now it says create a table of values below for the inverse of f of x equals 2 to the x. Well, the inverse, remember, with the inverse is we switch x and y. And so we have this idea here that if y was 1/8, now our x is going to be 1/8. And all we're going to do is switch here. What I would like you to do is pause the video and graph this. As you can see, does reflect over the line y equals x, and therefore the blue function that I just graphed, and you did also, is the inverse of y equals 2 to the x. And what we will find out is it's the inverse of 2 to the x is the logarithm. And so it says, what would the first step be? Well, we have y equals 2 to the x. We're going to try to algebraically solve the inverse, or find the inverse algebraically. And so step 1, we would write equals y equals 2 to the x. We switch x and y, so we get x equals 2 to the y. And now, where do we go from here? And that's the question that is, we don't know. We just have x equals 2 to the y. How do I solve for y if it's in the exponent? And that's what we're going to find out by using logarithms. And that's why logarithms are so important. It helps us solve exponential functions that we don't know how to solve. So let's take a look here. Defining a logarithmic function. The function y equals, and this is how we say it, y equals log base b of x. Let's see here. Y equals log base b of x. That's how we would write it, say it. Is the name we give the inverse for y equals b to the x. For example, y equals log base b, or 2 of x, is the inverse of y equals 2 to the x. So if the question is here, if we have y equals 2 to the x, how can we write the inverse of that if that was y equals log base 2 of x? Well, if we have, it already basically told us here, we had y equals 2 to the x, the inverse is y equals log base 2 of x. So if we go back here, we have y equals log base 2 of x. And so that's the equivalent function. Let's go a little bit deeper into that and understand why. Say b to the power of y equals x. So b to what power? B to the power of y equals x. And so one of the things that we look at when we say b to the power of y equals x, when I see something, when I see a logarithm, I see b as the base. See, it's the base here. Okay. I also see y as the exponent, and I see x as the result, or the answer. Therefore, I say b to the power of y equals x. One of the things that you should see is that the logarithm is the inverse of the exponential function, and exponential functions are the inverse of logarithms. This is what's extremely important here. So, without a calculator, how can we write this? Well, again, how do we say it out loud? 2, if I had x here, 2 to the power of x equals 8. So 2 to what power equals 8? So 2 to the power of x equals 8. Well, we think 2 times 2 gives us 4, times 2 gives us 8. So this would be equal to 3. Let's try this one. 4 raised to what power equals 16? So 4 to what power equals 16? Well, we know 4 times 4 equals 16, so that would equal 2. This is the idea. So when you have a logarithm, you're looking for the exponent. 5 raised to what power equals 625? It's the question. So 5 times 5 is 25, times 5 is 120, times 5 is 625. So this is equal to 4. Let's skip D for now. Let's go to E. 6 raised to what power gives you 136? Ooh. How else can I rewrite 136? And there's a couple ways to look at this. 6 raised to what power gives you 36 to the negative 1? Or, what if I wrote it like this? 1 over 6 to what power equals 1 over 36? Numerator is the same, so now I just need to look at the denominator. 6 to what power gives you 36? Well, 6 squared. So 1 over 6 squared equals 1 over 36. Well, and I have it right here, I kind of gave it away. When it's in the denominator, the power becomes negative, and so this is equal to negative 2. When you move something from the denominator to the numerator, the exponent becomes negative, and we talked about this in previous unit. Let's skip F for now. Let's try G. 5 to what power gives you square root of 5? Well, how else can we write a square root? You should remember that the square root can be written to the 1/2. Well, therefore, we just figured out that this is equal to 1/2. Pause the video, please, and try to do D, F, and H on your own. So welcome back. Hopefully you guys saw that D was 5. F, 2 to what power gives you 16? That's 2 to the 4th. And therefore, since 16 is in the denominator, we know it has to be negative 4. The exponent has to go to the denominator. And in this last one, hopefully you saw that any fifth root can be raised as 9 to the 1/5. Well, I still need it to be in terms of 3. The base is 3, so how else can I get 9? 3 squared? And then when you have an exponent raised to an exponent, you multiply, and so you get 2/5. So for number 3, the logarithm of base 2 of x plus 8 plus 9 was graphed on the coordinate plane. Which of the following would represent its y-intercept? What's the most important thing about the y-intercept? It implies that x equals 0. Whenever we have a y-intercept, the x is always 0. And so therefore, I'm going to look at this and then plug in 0 for x. So 0 plus 8 plus 9. So I have log base 2 of 0 plus 8 plus 9. Well, this is log base 2 of 8 plus 9. One thing that's what we're going to have to figure out, and it's got to become a little natural to you, is that when we see this, we have to think to ourselves, 2 to what power gives you 8? Well, we've already talked about this. 2 times 2 is 4 times 2 is 8. So this entire thing equals 3. So we have 3 plus 9. So y equals 12. And that's it. Choice 1. But again, you had to know two things there. What the y-intercept, what that implies for graphing, and then you had to figure out that log of base 2 of 8 is 9. Or, sorry, is 3. Next exercise before we look at the calculator is log base 3 of 40 must lie between which two integers. So when I think of this, I go 3 to what power equals 40? Well, I know 3 squared is 9, so what's 3 cubed? That's 27. And 3 to the 4th is 81. So what must it lie between? Numbers 3 and 4. And again, why? I looked and saw a log, and as soon as I see a logarithm, I just think the base to what power equals 40. And I realized that 3 to the 1st was 3. Well, that's not even close to 40. 3 squared is 9. That's not close to 40. And I kept going through it. Most calculators only have 2 logarithms that they can evaluate directly. One of them is log base 10, and that's called the common log. That is when the base is written 10. So when you do not see, and this is important, when you do not see a base there, see how the base is empty, there is none? You have to put a 10 in there. Okay, please understand that. You must put a 10 if there is no base. It's always the common base. The English math system is in base 10. And that's why it's called the common base. Now if you go to your calculator and just type in log, you'll see that log base 10 or log base 100 is equal to 2. And let's talk about why. 10 to what power equals 100? Well, we know 10 squared. And so we know that equals 2. If you use your calculator, you can get -3 here. And this one's going to be equal to 1/2 because 10 to what power is equal to 10 to the 1/2. Graphing and the domain and range of other logarithms in base 2 that we looked at in the previous 2 pages. What I would like you guys to do right now is fill in this table. So 3 to the -2nd, we know it's 1 over 3 squared, which is 1/9. 3 to the -1, can't even read that. One-third. Anything raised to the 0 power, we talked about that being just 1. 3 to the 1st is 3, and 3 squared is 9. Now I've said it multiple times, and hopefully you've got it, the fact that when we have a logarithm, it's the inverse of the exponential function, and so therefore all we're going to do is copy this. Let me put it in a different color. Let's copy this, but reversing the x's and y's. So what I'd like you guys to do right now is graph y equals 3 to the x and the inverse, log base 3 of x, on the graph paper right here, and make sure it looks like they're inverses of each other. So hopefully what you see here is that it is reflected over the line y equals x. And part of what we need to see here is what is the domain of y equals 3 to the x. So this is again y equals 3 to the x. This is the y equals log base 3 of x. What is the domain? Well, the domain is all real numbers. So either -infinity to infinity, or x is an element of all real numbers. It never stops. You can plug any x value in and you will always get an output. Whether it's really small or really large, any x value will work. The range, on the other hand, is no matter how small these x values go, I will always get a fraction that's never equal to 0. So we need y is greater than 0, or another way to write that is 0 to infinity. Well, when we think of inverses, and we know that log base 3 of x is the inverse of 3 to the x, these switch. So the one thing that we realize here with the domain, since they're inverses of each other, that the domain is x is greater than 0, that this green line, the log base 3 of x, never touches the y-axis. just like the orange line never touches the x-axis. And the range goes all the way down, goes all the way up, is y is an element of all real numbers, or negative infinity to infinity. And that will always be true of logarithms, no matter what the base is, as long as there's no transformation that occurs. So we're going to use our calculator. So how to graph on the calculator. So here's the calculator on my computer. We're going to go to y equals, since we're graphing, to get any log base, to have any logarithm that doesn't have a common base of 10, even though this one does here. We're going to go to math. We're going to scroll up. We're going to hit A. That's log base, and this is exactly what it looks like. So we have log base 10 of x. And then we can hit second graph to get the table. And so it says use your calculator to sketch log base 10 of x, label the x-intercept, and then state the domain. So if I look here, we have our range from -2 to 2. So I'm going to go to our window, and our x-min was 10, our x-max, or sorry, our x-min was 0, our x-max is 10. Our y-min, which is our range, just as a reminder on how to do that, we can sketch it here. Notice that our x-intercept, once again, there is no transformation that occurred, and therefore our x-intercept is going to be at 1. And if I look at the table here, luckily I have one that you can see the table together, you can see that it crosses 1 right after 8. So I know that approximately at 8 I'm going to be about here. I know at 1 I'm going to be here. And so I'm going to look something like this. That's a really poor drawing. Let's try this again. Something like that. You can see on the calculator drawn much better. Notice that there is an asymptote here. One thing that there is an asymptote here. It just doesn't show it. The logarithms on calculators do not show the asymptote. You must draw it. And therefore, see, you need an arrow there. You have to draw that, please. Okay? If you don't, it's wrong. So our domain, once again, is x is greater than 0 or 0 to infinity. And our range is -infinity to infinity, or y is an element of all real numbers. Okay? And said to label our x-intercept 1, 0. For exercise 3, it says which one of the following describes the graph and show how we made our choice. Well, what are the parts that we've talked about with the logarithm? Right here, this is called the x-intercept, and so we should probably be looking at that, but I'll even show you something sooner here. Notice that each one of these was transformed. Remember, this goes left or right, and this goes up or down. And so one of the things here is, where is the asymptote? The asymptote is at x equals -3. Where should the asymptote be on all the other ones that we've done? Should be here. So we know we moved to the left 3. So if we move to the left 3, we know that it must be either this one or this one. Let's move to the left 3. So since I know that it's either choice 3 or 4, I'm in a position where I can sit here and say, I don't know if it's base 2 or base 3. I can't really tell. They're both shifted down 1. So I'm going to pick a point. Let's pick this point right here, -1, 0. It's -1, 0. I'm going to plug into 3 and 4 to see if which one is true. So log base 2 of -1 plus 3 minus 1, does that equal 0? Or is it log base 3 of -1 plus 3 minus 1 to give me 0? So remember here, we're going to think 2 to the 0 power equals 2. But we have this -1 here. Well, we could add the 1 over, couldn't we? So 2 to the first power equals 2, question mark. Or, good, we could add this 1 over. 3 to the first power equals 2. And we know that then it must be choice 3. So again, how did I do this? This is just a logarithm. Well, we're not used to logarithms having this minus 1. So I'm just going to add it over to get log base 2 equals 1. This is 2 to the first power. 2 to what power? The first power equals 2. And we know that 2 to the first does equal 2, and therefore that's why it must be choice 3. So what this question, number 4, determine the domain, is looking at is this idea that you can only take logarithms of positive numbers. So let's just look here. Log base 2 of -1. 2 to what power gives us -1? It's a question. Can you raise anything? Can you raise a number to any power to give you a negative? Let's look up here and see. The green is the logarithmic function. Was there any way that this green was moved over into the negative x values? And the answer is no, because anytime you raise a number, if you look at an exponential, anytime you raise it to a negative, it's just getting smaller and smaller, but it doesn't ever become negative. Look up here when we did these. This one never became a negative. The domain was always x is greater than 0. So the answer here to can I raise anything to make a negative number? No. I can only raise this to as large of a negative number as I want, and this is just getting close to 0. It's never going to ever equal a negative number. And so what I need to do here, what you need to do, is whenever you have a logarithm, you need to say 3x minus 4 has to be greater than 0. The idea of this exercise is to show you that the inside of a logarithm must always be positive. And so when you add the 4 over and divide by 3, this is going to be your answer. You can never, ever have a logarithm with the inside, the of portion of it, be negative. And you can never have an exponential function equal a negative unless there is a transformation that happened. I know it says to write in set builder notation, in case you were wondering. That is set builder notation. All logarithms with bases larger than 1 are always increasing, because remember that the base is the exponent portion. So 1.1 raised to some number, it's increasing. If it was smaller, 0.9 raised to something, that would be decreasing. It's an exponential function that's decreasing. Finding the average rate of change is finding the change in y over change in x. So this is asking for f of 10 minus f of 1 all over 10 minus 1. And this is asking the same thing, f of 100 minus f of 1. All over 100 minus 1. What I would like you to do now is pause the video and you can use your calculator to find this. So what we see here is that from 1 to 10, is the slope very high? No, it's actually really small, 1/9. It's averaging just a 1/9 change. But even as we go 1 to 100, which is way over here, right? It's even smaller. And so as x gets larger, the slope becomes smaller. And that is it for today. So remember, key things here. Logarithms. Logarithms are the inverses of exponential functions, and logarithms give you the exponent. That's the key. Always think to yourself, in this case, 3 to what power will equal this? That's the key. Have a good day.